Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you. Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up. And check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Before we begin, a note from our sponsor. I'm Richard Jacobs, Executive Director of the nonprofit Finding Genius Foundation and host of the Finding Genius Podcast. In late 2016, I was rear-ended at 65 miles an hour by a truck on the highway, which sent me off-road into a ditch. The impact of the collision gave me a concussion and other injuries. At the hospital, a CT scan showed that I had thyroid nodules, which turned out to be cancer. It was then, when I had a biopsy of my neck, that I realized even if I was a millionaire, I wouldn't want a second or a third biopsy due to the pain and the invasiveness of it. And appointments at that time for thyroid experts were 3 to 6 months out. And I was worried about dying now, even if that was irrational. So because of this, I've decided to raise money to conduct a literature review on steroids, on the causes of anxiety and depression, a condition that affects well over 50 million people in the United States and hundreds of millions worldwide. Our goal is to create a codex, a guide that reveals all possible treatments for anxiety and depression for people that live with the condition, or for loved ones that have it, as my wife and my son do. To find out more about our fundraiser, visit findinggeniusfoundation.org and click on Current Initiatives. And now, to our guest.
Hello, this is Richard Jacobs with the Finding Genius podcast, now part of the Finding Genius Foundation. I have Chris Impey. He's a university distinguished professor, part of the Department of Astronomy at University of Arizona. So we're going to talk about his work and his research there. Chris, thanks for coming.
It's good to be here.
Yeah, tell me a bit about your background and how you got into physics and astronomy, and then I want to ask you about your current research.
Sure. So I'm a Brit, born in Edinburgh, and still have family back there. Lost the accent because we moved around when I was a kid. I did physics as the gateway drug to astronomy, so I was a physics major at University of London. So I did my bachelor's there, then went to Edinburgh for a PhD in astronomy, and then, being an astronomer, Britain doesn't have many clear skies, so I pretty much knew I was going to emigrate, and I went initially to Hawaii, University of Hawaii for a few years, great observatories there, and then to Caltech for 3 years. They had Palomar, what was before they had the Keck telescope, and then to Arizona in 1986. I've been here ever since as faculty.
Okay. And so what's your current research about?
Well, I've had a set of astronomy interests for 30 or 35 years, and then the last 5 to 7 years, I'd say I've started ramping up my educational research to the point where it's sort of eclipsing the astronomy part, because you can only do so much. So historically, I was interested in active galaxies, particular kind of active galaxy or quasar, where you get a privileged view close to the supermassive black hole that powers the object. I was also interested in gravitational lensing for a while, and then in ultra-faint galaxies, the kind of galaxies that represent very inefficient modes of star formation in the universe. And they're easy to overlook, but they actually can contain a lot of the normal baryonic material of the universe. So I've had a sort of range of topics. They're all extragalactic astronomy or observational cosmology.
What big questions are you currently trying to answer? And then we can delve into one of those or two of those.
Sure. I mean, the one in the work on distant galaxies and quasars or active galaxies is a question that's not easy to answer, even in a lifetime probably. It's sort of, we now know that galaxies all contain black holes, Milky Way being no exception. But most of those black holes are dark. I mean, they do grow over time, but they don't shine brightly, which would be a quasar. And so the question becomes, several questions. Which came first, the black hole or the galaxy early in the universe? How do the black holes get fueled? How do they get powered when they're bright? Why do they spend most of their time dark and not bright? And just the details of how galaxies and black holes have evolved in the universe. That's the sort of big research agenda. And I've, picked off pieces of that problem. There's dozens and dozens of people working on it, of course, because these are big questions.
So what do you mean? Like, how are black holes affecting the surrounding space around them, or their local, I don't want to call it a solar system, but black hole system, whatever planets are close enough to them, or other interstellar, debris that it affects them?
So it goes in two directions. I mean, black holes, sit at the center of galaxies, and it's not an unreasonable place to find a black hole because there's a mass concentration there. There are already a lot of stars and a lot of gas. Now, these are huge black holes. The type of black hole left behind when a massive star dies has 3, 5, 10 times the mass of the sun. These are black holes with millions of times the mass of the sun. And in our galaxy, it's a 4 million solar mass black hole, but they go up to 10 or 20 billion in some other galaxies. So these are monster-sized black holes, and they have enormous gravity power, and that gravity can pull material onto them. And so in the irony of black hole work in these situations, while black holes themselves, of course, are dark, nothing can escape, no light, nothing, their act of pulling matter in, devouring matter, and growing, which is what they do when they pull things in, accelerates that mass, and that accelerating matter emits enormous amounts of radiation. So the environment, the immediate environment of a black hole can be the brightest place in the universe, even though the black hole is dark. So that's one of the interesting things about studying them when they're fueling, when they're actively fueling.
What do you mean they're fueling? Like, what is the life cycle? Does anyone know what the life cycle of a black hole is? Not the end parts, but the beginning parts. How do they form?
The forming, the living parts and the forming parts can be dealt with differently. The forming is much less clear because the first galaxies happened only a few 100 million years after the Big Bang, so very early universe, very difficult to access. The Hubble Space Telescope is not able to get that close to the beginning of time. James Webb was actually built in large part to see first light, to see the first galaxies form. And so one of James Webb Space Telescope's agendas is to find the first galaxies and then also look to see if they have black holes in them. So that will help answer the question, which came first, the galaxy or the black hole? And the theory and the observation are just muddy on that point. It's not been answered yet, but it may well be with data in the next few years. And you can,
some of the mechanisms of black hole formation, I thought, is like collapsing supernovas. Certain stars of a certain size, when they collapse, they turn into black holes. Are there other methods, or is that the method, or it's just that's a supposition?
Yeah, that's the method for normal-sized stellar black holes. So when most people's awareness of black holes is focused on the kind of things that happen when massive star dies. And yes, a supernova goes off and it leaves behind either a black hole or a neutron star in the collapsed core. So that's a classical black hole, the kind of black holes we've known about for half a century. These other black holes that are at the center of galaxies are, in a sense, more interesting because they didn't form from any single event. They formed steadily over time. There must have been a seed black hole early in the universe when the galaxy itself was small. So galaxies and black holes have grown in tandem. The first galaxies in the universe were much smaller than the Milky Way, and they probably had much smaller black holes. So the black holes and the galaxies around them grow in tandem, which makes sense because galaxies, we think, grow by mergers and acquisition. So galaxies merge, collide, and grow over time, and then the black holes within them will merge, grow over time too. So the two processes run parallel. So we think we know the broad brushstroke of how that evolution happens, but the details, not at all, and certainly not that primary question of, did you have a seed black hole that aggregated a galaxy, or did you have a galaxy that grew its black hole, when a small black hole first, and then it grew steadily? We don't know that yet.
But why would a galaxy grow a black hole? Is there just a slow accretion of material that makes a black hole grow? So when it comes from its original, let's say, collapsing star, accretion over, I guess billions of years, can that grow a black hole to a monstrous size?
It can. I mean, the physics of that is now better understood. I mean, for normal, just to talk about them again and then set them aside, because I'm really not talking about stellar mass black holes, but stellar mass black holes, that process is well understood because the physics of a supernova explosion leads to a collapsing core, which will satisfy the condition of density to be a black hole. So we pretty well understand how normal black holes that are the massive stars form. In galaxies, it's a little different. Galaxies all have central concentrations. The center of our galaxy has densities of stars that are thousands of times higher than the density of stars around the sun. So very high star density, so very deep gravitational potential. It's a big gravity pit in the center of any galaxy. There's physics by which slowly and steadily over time, with stellar collisions and interactions, this concentration of mass, which is just stars and gas initially, can get to the point of being a black hole. And once you formed a black hole, you can just continue to fuel it and feed it because there's a lot of stuff there. And so it's natural to know that it will grow, and you can predict how fast it will grow. The question of why the black holes are mostly dark is an interesting one then, because it seems like there's a lot of stuff for them to eat, so they should be all active and bright, but they're not.
Yeah, that's weird. I mean, are we able to peer with telescopes into the center of our galaxy? And you said, I guess, the density is 1,000 times plus of what we experience in our solar system?
It's not with optical telescopes. So the center of our galaxy is opaque. I think 1 in a billion photons reaches visible light. Photons reaches us from the center of our galaxy because there's so much dust looking through the disk. So you have to go to longer wavelengths, which see through the dust and don't care about the dust. And so it's either infrared or radio or millimeter wavelengths. So all that we've known, the fact that we know our galaxy has a massive black hole and its properties and its mass and the orbits of stars near it, that's all come from infrared observations in the last few decades. And those technologies took a while to develop, so that's why it only happened in the last 15 or 20 years.
Well, what do you imagine it would be like if you were, on a ship and you were flying around in the center of our galaxy? Would it even be considered a vacuum, or would it be considered very, very low vacuum because of all of the matter that's around? What would it be like?
Even densities 1,000 or 10,000 times higher than the local density near the sun, there's still almost perfect vacuum. Intergalactic space is at 1 atom in a cubic meter, which is a billion times less dense than the air we're breathing. And in the middle of a galaxy, it's denser, but the density of matter is still, in an absolute sense, very low. But there's still plenty of stuff. I mean, what you would know, the most noticeable thing if you were living on a planet near the center of our galaxy, is the sky would be bright. There would be no night. I mean, there would be so many stars in the sky, and they'd be so near and so bright relative to our situation that it would never get dark. I mean, the night sky would just be ablaze with light. Not quite as bright as the sun, but just pretty much ablaze, and brighter than with a full moon or anything like that. So it would be a very different world. It would also be...
Would there be enough dust in the way, let's say I was on, again, some planet near the center of our galaxy, would there still be so much dust that even the starlight wouldn't reach me through my atmosphere and through the exterior?
Once the dust doesn't do its extinguishing thing except over large distances. So if you look through from our position, 2/3 the way out in the Milky Way, if you look through all the dust in the disk, you can see about 2,000, 3,000 light years. You can see quite a distance before the dust extinguishes the light. If you're in the center of the galaxy, the dust density is higher. But if you're assuming you're right near the center of the galaxy, yeah, you could see nearby stuff. It's not all extinguished by dust.
Interesting. Yeah, it's just fascinating what you said. I just wonder what it would, if anyone's modeled it, what it would look like. Would it just be like a kind of a hazy, overcast sky? Because of the dust and the, all the stars. I just wonder what it would look like.
No, it would be kind of gauzy light. There'd be sort of, because the dust is irradiated by stars, and so it glows dull red, or it reddens light behind it. So yeah, it would be probably a red, hazy night sky, but also embedded with a lot of light because there's so many stars too. So it'd be a totally different look for the night sky, dramatically different from anything we can imagine or have ourselves.
Would there be a lot of star-to-star collisions? Like, what would they orbit, or how would they move? How would the bodies move in this part of our galaxy?
So in the middle of the galaxy, and this is the work over the past few decades that led to the mass measurement of the center of our galaxy's black hole. I mean, the stars are essentially doing elliptical orbits in 3 dimensions around the black hole. So they're doing elliptical orbits, just described by Kepler's law, and we've tracked the orbits of dozens of stars that are near the black hole, which is an exciting thing to do. So the stars are orbiting that way. Densities 1,000 times higher than the sun, near the sun, doesn't mean stars bash into each other, because, I mean, a star in our part of the Milky Way, the size of a star compared to the distance between stars is factor of billions. So if you increase that by 1,000, it's still millions. In other words, the odds of stars colliding even near the center of our galaxy are quite low. I mean, in a human lifetime, it's not going to happen. You're not going to see it happening.
Okay. Interesting. So what are the physics of non-stellar mass or stellar mass sized black holes versus the gigantic ones? What's different about them?
I mean, the interesting thing about black hole physics is it's very simple. Black holes are actually, I mean, they're exotic and they're described only by general relativity, but they're physically very simple. They only have 3 properties. A black hole has a mass, it has a size, and it has an angular momentum, because they're almost always spinning since they form from objects that were spinning. And that's it. There's no other properties. And because the black hole's event horizon is an information barrier, you can't see inside, that limits you, and you can't say anything about the black hole inside. You can say what it ate or how it got to be the size it was or what it consumed to become a black hole. It's just a boundary. It's an information barrier. So in that sense, black holes are very simple, and the huge black holes in galaxies are fundamentally the same as the black holes left behind when a massive star dies. They're just bigger, more massive, and have a different amount of spin, presumably. We can measure it now.
So the physics of them are very different, or not really different, or the edges, is it different?
No, I mean, the physicists, the remarkable thing is they are so similar. Black holes are a unitary phenomenon. There's just very simple scaling laws that take you all the way from a few times the mass of the sun to tens of billions of times the mass of the sun. Nothing changes. That's extraordinary. Wow. There's no other area of physics where you can have a phenomenon describable fairly simply and in the same way that applies over a factor of billions of range of mass or scale. That's really unusual.
Yeah, that's cool.
So that's good. I mean, that makes the phenomenon at some level simple, because the scaling laws are so simple, and they're fundamentally the same object. And the interesting thing, of course, is that nature makes black holes with such an enormous range of mass.
So I guess that would say that the interior structure, if there is such a thing of a black hole, regardless of its size, is probably uniform, or maybe there's almost no structure at all.
There need not be any structure. I mean, theorists, of course, like to speculate about this, given that observers have no information. We have no data to bring to bear on it. So there's speculation about what happens inside a black hole, what the physical conditions are. Especially if it's rotating, you can have some interesting phenomena. But it's pure speculation. So, I mean, I'm an observer and a scientist who likes to work with data. So I let you let the theorists have their speculation, but at the moment, that's all it is.
Does anyone suppose there is any structure, to the inside of a black hole, meaning everything within the event horizon?
I mean, sure. This is pretty much in general relativity, so it's not an outrageous extrapolation of the theory. But a non-spinning black hole should have a singularity at the center, and that's a problem because the singularity is an infinite cusp of density. So mass density is infinite, and that's unphysical. That says your physics is wrong. And Stephen Hawking famously called this black holes that contain the seeds of their own demise, by which he meant the singularity, which is a prediction of black hole theory, is telling you that the theory is incomplete. So the fact that we can't have a theory of black holes and how they form and we can describe them physically should not conceal the fact that the theory is definitely incomplete, because singularities make no sense in physics. So that's a non-spinning black hole, stationary one, which we don't really think exists in practice because everything that forms a black hole will have angular momentum, so they'll all be spinning. When a black hole is spinning, it's possible that the singularity turns into a ring, which is almost logical that it might do that. And the ring is therefore its infinite mass density, but extended into a ring, which is equally weird, really, and it's still a problem for physics. And if you look at the physics of time on that ring, then the space-time properties are very interesting because it's what's called a time-like curve. And the time-like curve means if you could travel along that curve, along that ring, you could move forward and backward in time at will. So people, when people are hyperventilating and speculating, way beyond what we can test, they'll say, well, if you could go into a big black hole, one that's spinning, and find the time-like curve, you could spend forever up going backwards and forwards and meeting past and previous versions of yourself and future versions of yourself by a time machine. It's like a time machine, essentially.
Right. But even getting there is insane. It's so far
so getting there is...
and you'll be torn to pieces, and then.
But not actually. That's another good thing about the big black holes. So if you work out the tidal forces, the stretching forces of a physical object falling into a black hole, when it's a star, a dead star, it's hopeless. You'd be ripped apart at the level of molecules and fibers and atoms and tendons. It'd be a very, very nasty way to die. However, when you take those same very simple scaling relations and you just go up to bigger and bigger black holes, their mass increases, but the tidal force is a differential force, and it actually goes down. So the tidal forces of the biggest black holes are much less than the tidal force of a dead star black hole. And the boundary is about 10,000 times the mass of the sun. So for anything bigger than that, which includes all the black holes at the center of galaxies, you could fall into them without being torn apart. In other words, in principle, you would survive falling in. And then you would be able to be in a black hole, and you'd never be able to tell anyone what you saw because nothing can get out. So it's a one-way trip.
I've heard black holes move, though. So, like, if a black hole is in a particular part of space and it moves, what does it, quote-unquote, leave behind? Regular vacuum?
Well,
does it vacuum up stuff? Like, does it, what?
It's moving through space because it had however it formed, it has a space motion, and it just continues with that motion. And it will, yes, as it encounters material, if that material could be swept into the event horizon, make the black hole grow a little. But again, the density of matter in most parts of space is really low, so black holes are not going to grow a lot that way or very quickly. But yes, black holes are all dynamic objects. The dead stars especially, they all had motions before they became a black hole, and those motions continue. In a galaxy, it's different because the galaxy's black hole is at the center of the galaxy, so it's stationary within the galaxy and doesn't go anywhere or move.
It doesn't move at all?
Well, it spins, but it won't move. It's at the center. It's like imagine a gravitational pit or a deep well. You're at the center of the well, and you can't go anywhere else.
Does it oscillate around the well, or it literally just doesn't?
It might do that a little because, if it's just a single isolated big black hole at the center of a galaxy, it'll eventually just settle and, not go anywhere. But black holes and galaxies grow by merging, as I mentioned, over cosmic time. And when two galaxies meet and their black holes merge, that's interesting because then they do orbit around each other for, millions or tens of millions of years. You can even get a situation where the dynamics are such that one black hole will eject the other one from the galaxy entirely. So you could have an isolated massive black hole just sailing through intergalactic space. So when there are mergers of these big black holes, interesting things can happen.
Yeah, again, when a black hole moves or is forced to move, what does it leave behind?
Well, it doesn't leave anything behind. A black hole is, the best way to think of it is just an indentation in space-time. That's all it is. It's basically a space-time artifact or feature. And then the other material that happens to be in that space-time, gas, dust, normal stars, just goes about its business but responds to the gravity of the black hole.
So it's changing the nature of space-time in the same way a planet would, or in a different way?
In fundamentally the same way, because the theory describing all of those is general relativity. So the premise of general relativity is that mass and energy, so mass energy bends space-time. And if it's a planet, the density of a planet is just low. It's not a very big number. The density of a star, or even the center of a star like the sun, is also not a very big number. The sun is not much denser than iron in its core. So these are objects, planets and stars, that just don't bend space-time very much and put the tiniest little dent or dimple in it. And black holes are objects so extreme that they literally pinch off space-time, if you want to visualize it that way. I mean, the math of it, of course, is different, but it's essentially the same thing. It's saying that they create such a rip or a dent or a rift in space-time that they seal their little part of it off from the rest of the universe.
So again, when a black hole moves, in the case that it does, what it quote unquote leaves behind is just, it looks like space-time is just back to the way it was. It's essentially like an elastic process. It was warped and then it goes back again.
Yes. I mean, it's right. It's moving through space-time and it's distorting space-time as it moves. These minor, so it's mostly elastic process, as you say, but the minor exception to that is anytime the mass configuration changes for whatever reason, like it interacts with other matter, or maybe rotates, or maybe it's a oblate black hole, so it's not spherically symmetric, then you get gravitational radiation. And gravitational radiation, of course, emits is more space-time ripples moving at the speed of light away from the black hole. So it's not a completely passive aspect of space-time when there's activity or motion or mergers or other phenomena happening.
But has anyone observed again the space where the black hole used to be, and do they can they tell anything about it that's different?
No, I mean, it's not going to leave an imprint on the space-time where it's no longer in a place where it's no longer there. The black hole is the place where the space-time is distorted to the point of being pinched off, and the place where it isn't is just normal space-time. So there's no trace, if you like, of where it was, just in space-time itself.
So does it create, you say pinched off, so does it create like a temporary, mathematically impossible discontinuity in the nature of space-time? So let's say an event horizon or something? It
is, event horizon is not a mathematical impossibility. The singularity is a mathematical impossibility. So that's the problematic element of a black hole, as predicted in general relativity. It's not understandable in the theory itself. So that's a problem, and that's what Hawking meant when he said the theory is incomplete. We don't really understand black holes, and that's true now. 50 years after he said that. The event horizon is just a mathematical definition of the region within which everything is trapped and nothing can escape. It's not a physical barrier, or it's an information barrier, an information membrane, if you like, one-way membrane.
Okay. The pictures that came out, I think it was like M365 or something, the black hole that was, first visualized or reconstructed from data. Did that tell you or other researchers anything new or different?
Well, these first few images of black holes and their shadowing of black holes and their accretion disk, I mean, they've been exciting because we've never had such images before. I mean, people forget. They see the picture in the paper on the web and they think, oh, it's a picture. Well, again, it's not an optical image. It was made with a radio telescope, and just the colors, the radio emission was turned into a color. So they're long wavelength observations, but they're amazing, those pictures, and they've been used to test general relativity in ways that has never been tested before and at new levels. And it's passed all those tests. So when we have a model or a theory like general relativity, you always want to push it to its limits. It's been around 100 years and it's done very well, but these kind of black hole data tests it in a completely new way, and it's very interesting that it's survived these tests so far.
I mean, did it tell you anything specific or no?
Well, they were telling, I wasn't involved in that particular collaboration. They've told us they've told us mostly about the immediate environment of the black hole. They told us about what the accretion disk, this hot disk of plasma that's around a black hole that sort of funnels eventually into the black hole through the event horizon and becomes part of it growing in mass. So they've told us how that works in particular. They've also told us how the shape of the event horizon changes with the rotation of the black hole. The Earth is not quite spherical because it's spinning. It's oblate, and so black holes are oblate too. But the way they deviate from spheres is interesting and not easy to predict actually, and it's only ever been measured in the last few years.
Oh, what do they look like when you say they?
So they do look oblate, like a squashed sphere, and then in the way you might imagine that the equator of the spinning black hole is wider than the other dimension. So that's useful. I mean, and then the most interesting things are really what's coming out of the orbits of these stars that are very near the black hole, because they're little test particles, each of these little stars, because the central black hole in our galaxy is 4 millions of times bigger than they are, so they're almost like massless little test particles. So we've learned a lot just from how those orbits work and how stars orbit near a black hole. So there's a whole raft of things. I mean, it's pretty esoteric tests of general relativity. The basic theory is intact; It hasn't changed.
But I mean, can you estimate the form or the shape of the singularity in it?
No,
based on the observations of the accretion disk.
No, unfortunately, the singularity is a cipher. So the problem with this is the good and the bad news about black holes being so simple. The good news is they're simple. They have 3 properties and that's all, and they scale universally across all these masses with the same physics. That's the good news. The bad news is you don't get other information because the event horizon is a barrier to knowledge. So we can't say anything about the conditions inside the event horizon, about whether the singularity actually exists, because it's only a prediction of general relativity. No one's seen one. And so, yeah, there's a lot we don't know, and probably we can never know, actually.
So, I mean, I guess coming back to your research then, what are you hoping to figure out about black holes?
Well, my work is more on the statistical properties of galaxies and black holes and how they grow. And I'm sort of have been most interested in the question of why, when there's so much material at the center of a galaxy, why do black holes seem to spend 90 to 95% of their time dark? It's like, they're a massive, starving, hungry person in the middle of a larder or full of refrigerators and food and provisions, and they're not eating. It seems that the answer is that it's a binge and purge thing. So black holes do take a while to accrete material. It doesn't just fall right in, and they don't just suck in stars whole. That sort of mental image of them just tearing up stars and devouring them like M&Ms, that just doesn't happen. It's a very slow process. However, when they do it, what happens is the death throes of the material falling into the black hole create such energy that energy creates shock waves and plasma that blows away the material. So the feeding frenzy of a black hole, when it happens, creates such energy output that they essentially clear out their surroundings. So they sort of evacuate a region around them, and then they don't have any fuel, and then they go dark. And it takes, just in natural time scales of particles moving in orbits, it takes millions of years, hundreds of thousands, millions of years for the matter to aggregate back in and for the black hole to start fueling. So it's a cycle where there's small, intense bursts of activity followed by long, dark periods where the black hole is quiet because it's not really fueling.
So when it's in a quiet period versus an active, devouring mode, are the physics very different? Is the black hole very different, or is it just, so simple it's boring and it's kind of doesn't have
it's
much action?
Different physics. The black hole itself is simple. It stays the same. It's impervious to its surroundings. It just has the properties it has, and that's it. But its environment, yes, changes. So these accretion disks that are almost universally found around not just black holes, but all sorts of compact objects, other kind of compact stars too. That's where all the interesting physics happens, because this is a hot plasma, millions of degrees, moving in very rapid orbits, not near the event horizon, about 10 times out from the event horizon, so it's pretty close, but not super close in. And it's a particle accelerator. It's a fantastic particle accelerator. So these black holes can create jets that can, penetrate and leave an entire galaxy and go through intergalactic space. These jets accelerate plasma to 99% of the speed of light. So just phenomenal energetic physics caused by black hole accretion. That phenomenon is behind a lot of interesting physics. And it's difficult physics because there are magnetic fields involved. So to understand it, you have to do what traditionally is one of the hardest things in physics, which is three-dimensional magnetohydrodynamics. That's just an evilly difficult thing to do, even with a computer. So it's an interesting challenge for physics to fully understand what's going on near a black hole, because it's just massively complicated physics. You've got to have particles in there, you've got gas in there, you've got magnetic fields, you've got general relativity. All the calculations have to be general relativity, which is hard on its own. And so it's a tough one.
What questions do you think are answerable maybe in the next few years, or all this stuff is just so difficult that who knows?
Well, James Webb is hopefully going to answer the chicken and egg question: which came first, the black hole or the galaxy? I think it won't do it in the first data release next week or in the first year or so. That's a long-term project, but that's part of what it was built.
How will it do that, by the way?
Because it's an infrared telescope, so it's able to see to the redshifts or back, with the expanding universe. When you look within 5% or 3% of the Big Bang, you're looking at light that's been stretched by the expanding universe by factors of 20 or 30, and so you actually have to have an infrared telescope to measure that radiation. Hubble can't do it, and Hubble ran out of steam well before getting to this early age. So James Webb is a bigger telescope, of course, 6.5 meters compared to Hubble's 2.8, 2.5, and it's working at the right wavelength. So it's much more effective tool. So it can see, in principle, it can see the earliest possible galaxies we can imagine forming. Galaxies can't form instantly. It takes a while for that size of material to collapse by gravity to form anything from a smooth gas. So I'm pretty confident that James Webb will be able to see the first phase of galaxy formation. And the signature of a black hole, even a smallish black hole like 100 times or 1,000 times the mass of the sun, is quite different from the signature of a small galaxy. So you should be able to distinguish the two.
Very cool. Chris, where's the best way for people to find out more about your work? Where can they go?
I mean, I think it's chrisimpey-astronomy.com. I mean, I have a website, and my university website gives a list of my research interests. Like I said, I've been migrating towards educational research soon, science literacy, and using neural nets to detect fake science on the internet automatically, that kind of stuff. So that's taking more and more of my time, actually.
Okay. Well, very good, Chris. Thanks so much for coming on the podcast. I appreciate it.
Okay. It's good to talk to you.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.